right, welcome back. This is part 2 of our series on adding crazy vectors together at a bunch of different angles. So in order to do today's, we're going to take a look at adding multiple vectors together, and then we'll take a look at adding vectors together at angles. So that's kind of where we're going today. And in terms of this, there's a couple things you should remember from the last video. Number one, SOHCAHTOA, right, that we can use basic trigonometric identities or relationships to find missing signs of triangles. Pythagorean theorem is also important. But one of the big ones I want to mention to you is to remember that when we are adding vectors together, that A, we always need to add vectors together tip to tail. And then B, the order that we add the vectors together doesn't matter. So we said, 2 plus 3 is equal to saying 3 plus 2. We're going to take advantage of being able to sort of move our vectors around a little bit in order to sort of cheat the system a bit. And again, the reason why we're doing this is to help us avoid lots of really nasty trigonometry, but because it actually works. And so we're going to take a look at how this works with my little treasure map that's on here. So if you can see, I've got a little treasure map here that says, go north 10 miles and then go to the east 20 miles. Then you go north 5 miles, then you go back 10 miles to the west, and then you go due south at 25 miles, and you will find the treasure. So if you want to solve this and find the treasure, and you don't want to walk this whole path, there's a couple of different ways that you could approach this. Method number one would be to draw this as a scale map, and we could call this, solving vectors graphically. You could draw this as a scale map, and then all you would have to do is look at the resultant vector, which we would draw from the beginning to the end, or we would say from the tail of the first vector to the tip of the very last vector. That's our resultant vector. So if we take a look at this, we kind of know where our resultant vector's got to be. Regardless of all the other, crazy loopy paths that we take, the resultant vector is actually from here to here. That's it. Regardless of all the rest of the path, the resultant vector is the net of all of those different pieces together. There it is. So that's our resultant vector right there. So in terms of finding this, if you did this graphically, like I said, you could sketch it out on a piece of graph paper. You could measure it all with a ruler, make sure that these were, 10 miles equals an inch or whatever that you did. Then you could literally just draw this and measure it with a ruler if you're done. And you could kind of figure out what this angle would be and say, hey, well, I'm not going through that whole path. I'm just going to turn around and go from here. That would be nice, right? If we could do that. A lot of times we really can't draw it as a true treasure map when we're talking about forces and things like that. But we can still take advantage of this fact that the resultant vector is literally just the net of all of these pieces added up. And we can take advantage of the fact that when we add our vectors together, we can add them together in any order we like. That makes our lives easier. So let's take a look at what this is. We call this using vector components, P-O-N-E-N-T-S. What we're really looking for is, if I knew this vector, really all I need to know is, all right, how far down do I need to go? And how far to the right do I need to go? Components. This is the sum of the y components. And this one right here is the sum of the x components. Now, these are nets because we've got positive and negatives on there, but this is called the vector components technique, and it works great. So let's take a look at what this is when we're actually doing like real life things here. Let me switch my tool here. If I have my vectors, here's my starting vector. Okay, I got 10 meters. Come here. I got 10 miles up, and then I would go another 5 miles up, and then I would come back down 25 miles. If I did this, what truly is my net of this up-down motion? This is plus 10, this is plus 5, and this one over here was minus 25, right? Those were my values that I had. So my resultant vector starts at the beginning and ends at the end. So it's actually this way. And if you know what this is, right, plus 10 plus 5 is 15 up, and then 25 down gives me a net sum of negative 10. I would literally just say my sum of my y's is equal to plus 10 plus 5 minus 25, and that equals negative 15. Again, you can see it graphically, but mathematically it also works. So if we're using forces or something like that where we don't have a pretty picture, we know what the sum of our y's are. So the sum of my y's is right there. There it is, negative 10. Oh, sorry, I should label that. So the sum of my y's. How about my x's? Well, we only had 2 x's in this one. So there's that. I go to the right, 20, and then I come back to the left, 10. So when I add these two guys together, if I add my sum of my vectors up, this is plus 20, and this is minus 10. So start here and then end here. This means that my resultant vector is this direction. The sum of my x components is equal to plus 20 minus 10, which is also equal to plus 10, 10 to the right. So my sum of my x's is also 10. So now I know what these values are. The sum of my y's is negative 10. The sum of my x's is positive 10. If you notice, the directions are actually the right way. I know what they are. And if you even look at my drawing here, they even look like they're about like that. So I can figure out the sum of my y's, the sum of my x's. Figure out the sum of my x's and then the sum of my y's. Doesn't really matter which one I do. But by looking at these components sort of one piece at a time, just the uppy-downy parts and just the lefty-righty parts, I can still get the exact same resultant because it doesn't matter what order I add them in. So I'm going to add them in the order that's easiest for me, all the y's and then all the x's. And then all it is a matter of Pythagorean theorem. So I'm going to kind of erase some of this extra, erase some of this extra writing that's on here. So I know what some of my y's are. I know what some of my x's are. I'm going to get these guys kind of out of the way. If I can get them out of here. So when I want to solve my final triangle to figure out what my resultant vector is, well, I know some really good basic stuff like Pythagorean theorem. The sum of my x's plus the sum of my y's equals my resultant. A squared plus B squared equals C squared. Call this one A, and then this one is B, and then this side would be C, right? If you remember that. So the sum of my x's plus this is squared, plus the sum of my y's squared equals my resultant squared. So we can just kind of solve it, figure out what it is. 10 squared plus negative 10 squared equals r squared. Well, this is 100, and this is 100, so this is 200 equals r squared. That means that r is equal to the root of 200. Now, okay, good news for you. Not a math teacher. I don't care if you leave it in radical form. In fact, please don't leave it in radical form, because if you take the square root of 200, you're going to get a number. If you were a math teacher, you would say, well, okay, so class, this is actually root 2 times 100. This is a perfect square, so the actual value of this is actually 10 root 2. If you tell someone to go find the treasure by going 10 root 2 miles to the south, they're going to be like, what in the, what, huh? It doesn't make any sense, right? So don't. Just use your calculator. Please, just use your calculator. So what is the square root of 200? 200 second square root. If I do this right. I don't know what I just did. God, I keep hitting the matrix button. 200 equals, if I actually figure out what this value is, r is equal to, oops, sorry, pen. R is equal to basically 14.142 something or other like that. So basically it's 14 miles, something along those lines. Okay, so again, don't worry about leaving it in radical form. Just figure out what it is. So we now know what this value of r here is. It's equal to about 14 miles. If I go 10 miles to the south and 10 miles to the east, I'm going to be going about 14 miles. So now angles. This is the other important part to make sure that you actually finish up. Now, in this one, it's a little bit easier, but in general, you also need to be specific about what the angle is. When I say being specific about the angle, hold on, you have to do two things. Number one, you have to give me the degrees, and number two, you have to give me the direction. Direction is something like east, south, or more normally south of east, or something along those lines. So how do I figure out the angle? Well, this is SOHCAHTOA. This is where you figure out what the angle is. Now, where do I define my angle? Okay, in order to figure out where you define your angle, your resultant is here. It starts here and ended here, this way, towards the treasure map. That's the direction of it. Always define your angle from the starting point. In other words, from the tail of the resultant vector. Because if I told you to turn 45 degrees from where you finish, I don't know where I'm finishing, right? You always define angles of resultant vectors from the beginning, the starting location. That means I need to define this angle is going to be my theta. Okay, so if I want to figure out what my theta is, what pieces do I know of my triangle? Well, now I know all three of them. I know both the adjacent side, I know the opposite side, and I know the hypotenuse. Typically, we use tangent. We use our original values just in case we made a mistake here. So typically, we use tangent to find what our final angle is. And so tangent is this. Tangent of theta is equal to opposite over adjacent, TOA, right? Our opposite side is the sum of my x's. In this case, the adjacent side is the sum of my y's. Okay, this is not an always formula. It's not always the tangent of the angle is x over y, because sometimes our angle's in a different spot. Sometimes we're defining this angle or something else. So don't try to memorize that. Look at your triangle and pick your x's and pick your y's. So in this case, my tangent of theta is equal to the sum of my x's, which is 10, over the sum of my y's, which is negative 10. The angle really doesn't matter. So the tangent of theta equals 1. And again, I know you may recognize this as an equilateral triangle, or not equilateral, isosceles? What do you call it when it has two equal sides? Anyway, that one. You may recognize that it's a 45-degree angle, but practice putting your values in there so that you can actually get the right answer. It's also a good check to make sure that you're not in radians. So in order to do this, I would do the inverse tangent, because I have to kind of untangent this. So it's kind of like taking a square root, I guess. So you would type this into your calculator of the inverse tangent of 1. You cannot say that theta equals 1. You have to take the inverse tangent of it in order to get the theta by itself. So again, it's usually the second key and then the theta or something along those lines. And what it looks like in your calculator is this. I believe it's called arctangent, by the way, is the fancy name of that. The second and tangent of 1. It looks like that on your calculator. So you can kind of see where it says tangent to the negative 1 power. That means I'm like inverse tangenting it. I'm untangenting. And the answer to that is going to be, if you've done it right, 45 degrees. If you do your calculator check right now, you don't get 45 degrees. You're probably in radians. So 45 degrees. So now we know a variety of things. We know how long our resultant vector is, 14 miles. We know the angle that we should set out, which is 45 degrees, but we don't know the direction that we should set out. So it's magnitude, angle, and direction, because it's 45 degrees, but which way? 45 degrees from north, 45 degrees from east, etc. You have to say the direction. In this particular case, it is 45 degrees from due south, right? Due south is that line that we've got drawn there. So now is it 45 degrees to the east or to the west of due south? And it's important to say that. In this particular case, you turn 45 degrees to the east of south. So our final answer to our resultant vector equals 14 miles at 45 degrees to the east of south. Again, that gives you the full description of what our resultant vector would be for those particular things. It's kind of a lot. I know. You may want to hit pause and rewind that and go, what the hell did you just do, Bedwell? So here we're going to take a look at an example where we're applying this to some vectors that aren't straight uppy, downy, lefty, righty. Because it was really easy. In the first one, we already had all vectors that were vertical and all vectors that were horizontal. In this one, we don't. But, and here's what we're going to typically do more often, is that we can turn this into x's and y's. And this is the important part. So number one, let's take a look at where our resultant vector would be. Our resultant vector is going to be from here, the start, to here, the finish. So we now have a pretty good idea kind of what direction our angle is going to be heading at. And if you keep that in your mind, that helps you kind of interpret your answer. That's a resultant. A resultant is going to be long, right? If this one is 10 miles at 20 degrees north of east, and this one is 20 miles at 30 degrees south of east, this is going to be longer than either of those two. So I know my resultant answer has got to be greater than 20 miles. And I know that my angle is still going to be heading in that kind of south of east sort of direction. So I can still kind of analyze sort of what direction it's going to be, and now I can kind of get the specifics. By the way, 20 degrees north of east, that is this angle, 20 degrees north of east. And this one that's 30 degrees south of east, that is that direction. That's that angle, 30 degrees south of east, just in case you're wondering where those labels came from. Okay, so now we kind of know, like I said, we've got an eye on sort of what our resultant vector is going to end up looking like. So let's figure out how do we address this. So again, I'm gonna kind of, where am I gonna draw it? I'm gonna draw it kind of like, I don't even know what that is. Sorry, pen. It's gonna be that direction, right? Something like that. That's kind of our result. That's fairly close, just to give me an idea of what I'm aiming for with my final prize. Okay, so now in this particular situation here, we don't have X's and Y's. Where's my pen? Dang it, there it is. We don't have X's and Y's, but we can make this into X's and Y's. So here is a triangle. Let's see if I can draw it really gently here. Here we go. This is an X, and this is a Y. In order to do this particular vector, this one that's up here, we can call this our A vector if you want to, we have to go over X units, and we have to go up Y units. That's what this is. So we now know something about this triangle here that we can actually figure out what the X component of this A is and the Y component of this A is. Because we know what this angle is, 20 degrees, and we know how long this is. So we now have a triangle. I'm going to draw it over here a little bit bigger. Here's our Y, here's our X, here's our A. We know that this is equal to 10. We know that this is equal to 20. And now we can use SOHCAHTOA. I'm going to sneeze, I believe. Woo, that was exciting. So now we can use SOHCAHTOA to figure out our X and our Y components. So how do we do this, right? Here's our angle. Well, the sine of 20 degrees equals opposite over adjacent, right? SOHCAHTOA, right? So the opposite in this case is the X. The hypotenuse, did I say adjacent? Sorry. So SOH, opposite over hypotenuse. The hypotenuse is our A vector. So we can solve for this because sine of 20 is just a number. And then we know the value of A. It's 10 miles. So basically it's the sine of 20 degrees times A equals X. Well, enter it into your calculator. The sine of 20 degrees times 10 miles. Again, this is equal to 10 from the problem. So the sine of 20 times 10 is equal to 3.4. I'm going to keep it with 2 sig figs today. So we know that this one right here is 3.4. Oops, sorry, I wrote it in the wrong spot. It's our X component. 3.4 right there. Again, sine of 20, opposite over adjacent, or over hypotenuse. It's the A that keeps throwing me off, sorry. So then to figure out the Y component, we can now use cosine. Because we know that the cosine of 20 degrees is C-A-H, adjacent over hypotenuse. In this case, our adjacent is the Y component, and the hypotenuse is our original vector. So the cosine of 20 times A equals Y. Well, again, A equals 10 because that's the length of our original vector. So we take cosine of 20. Cosine of 20 times 10. And this one is like 9.4. So now this one is 9.4. So all I did was I took this little triangle, this vector, and I turned it into the X and the Y components. Oh, and I've mislabeled everything as Y and X too because I'm brilliant. Oh, man, I'm having one of those kind of days. Because the X components go lefty-righty. I've got them in the right spot. I just labeled them incorrectly. My apologies. This is the X. This is the Y. Sorry. Y's are uppy-downy. Nice me. We're going to do the same thing with this other one. So for this green vector, we're going to do the same thing. I want to know the Y component of our green vector, and I want to know the X component of our green vector. So let me pick that color here so I can switch over to it. So for our other vector here, we want to know this one. Go away. To this one. There's our two parts of this particular vector. In order to do that one, we have to go down a certain number of units, and we have to go over a certain number of units. So here's our Y, and here's our X. Again, down and then over. So again, your case in this point, we've got to be a little bit careful in terms of labeling our angles. Remember I said our label here was 30 degrees, was here, south of east. This angle right here is not 30 degrees. The inside of this triangle is not 30 degrees. Can't remember if this is complementary or supplementary, but it adds up to 90. So our inside triangle here is 60 degrees. That's this angle right here, not the outside one. So you got to be thoughtful kind of about how you plug these things in. So now you should be able to hit pause, do SOHCAHTOA, figure out the length of your y and the length of your x. So I'm going to draw it down here. Here it is. We're trying to figure out this y and this x. Y and x. So this is our second vector. We know what this is. We know that this equals 20 in this case because that was our original length of that vector was 20 miles. So in order to figure out my x component, I would do the sine of 60 degrees, again, inside there, is equal to opposite over hypotenuse, which is x over b, or whatever you want to call it, h for hypotenuse. So the sine of 60 times the length of our b vector gives us the length of our x component. So let's see what we got here. Sine of 60 times 20 is equal to 17.32. So I know that this x component is 17 miles, basically. Again, I'm keeping it with just two sig figs. Now we can do the y component. If we use sine for one of them, we use cosine for the other one. So the cosine of 60 degrees, cosine of theta, equals adjacent over hypotenuse. The adjacent in this case is the y component. The hypotenuse is our vector. So the cosine of 60 times b equals the length of our y vector. So cosine of 60 times 20, which is the length of our b vector, is equal to, well, it's because the cosine of 60 degrees is 0.5. The angle here is equal to 10. Again, so you can see I did sine and cosine of each one. So this triangle here is 17. This side of the triangle here is 10. So now we just figured out the x and y components of each of our two vectors. Well, so now what? Well, now we just have to add those up, just like we did in the other one. We add up our x's, and then we add up our y's. This is the key part with doing this. When we're doing our resultant vector is the sum of the y's plus the sum of the x's. Again, I've got my original resultant vector way up here, just so we can kind of see it. But it's the sum of my x's and the sum of my y's. Now, again, they're a little bit different directions. Some of my y's are up and some of my y's are down. So we have to be a little bit careful about direction on this. So I'm going to go back and label the directions on here. So my x, for this one, I'm looking at my a vector here. This one right here, it's going to the right. So my x is positive, and it's going up. So my y is also positive. My x is positive, my y is positive. For my other vector, in this case now, I am going down. Give me my pen. My y here is negative. Again, it's negative going downwards. My x is going positive. So this is negative 10. And this is positive 17. So in order to figure out my overall directions, I add up the sum of my x's and the sum of my y's. Because what I want to find for my resultant vector, the sum of my y's and the sum of my x's, right? So this is the sum of my y's, and this is the sum of the x's. So if we want to do this, this is Pythagorean theorem. But that's a hard one to make that connection. We break each vector down into its x's and y's, and then we recombine them, x's first and then y's, to figure out what our sums are. So what is the sum of our x's? Well, the sum of our x's, we've got plus 9.4 from the first. We went to the right, and then we went to the right even further. So this is 9.4 plus 17. Those are the x's, the x components, and they're both positive. By the way, we have to do squared, 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 Pythagorean theorem. The sum of our y's. This is now up 3.4, and it's down 10 squared equals r squared. Again, one of the y's goes up, the yellow one, but the green one comes back down. So we've got to be a little bit careful with how we include those negative signs. The directions, again, are important in terms of which way you're facing. So now it's Pythagorean theorem. 9.4 squared plus 7, oops, sorry, no. Back up, Edwell. 9.4 plus 17. And then I can square that. So this is 26.4, 26.4 squared plus 10 minus 3.4 gives us a value of negative 6.6 squared. That just means down equals r squared. So 6.6 squared plus 26.4 squared equals 740.52. That equals r squared. I need to take the square root. Wow. If I can't answer or use my calculator correctly, that would be really helpful. It looks like r is equal to 27.21249. So 27 basically with two sig figs to it. So this would be miles. Okay, that means our r here is 27 miles. I know this is a lot. This is hard to do this. We'll be practicing these. So now what? You're like, I don't even know what the hell we're doing right now, Bedwell. I get you. So now we figure out how long our resultant vector is, but we haven't figured out what direction to go. That's what we need to do. The other part, figure out what direction are we actually going. Okay, so in order to figure out our direction, we have to figure out the sum of our y's, sum of our x's. We're going to use SOHCAHTOA. Get rid of this stuff so I have some room to draw here. So I shouldn't have erased some of that stuff, but it's okay. Okay, so to figure out what the sum of our y's and the sum of our x's are. Remember, the sum of our x's were 17 plus 9.4, which was 26 point something. This one we decided was 26.4, the sum of our x's. We decided that the sum of our y's was negative 10 plus 3.4. The sum of our y's, again, 3.4 up and then negative 10 down, which gave us a value of negative 6.6, and again, negative because it's going downwards. And then we can use SOHCAHTOA. I'm going to get this out of here so I have a chance to move it. I know this is a lot. We will do this in class. This takes a while. Okay, so the sine of our angle, which we don't know, we're trying to find, is equal to the opposite over the hypotenuse. Well, the opposite side in this case, if this is our angle that we're trying to find, again, angles from the beginning, our opposite side here is the sum of the x's. And our hypotenuse is the resultant vector. So the sine of theta is equal to 26.4 divided by 27. Again, 26.4 was the sum of our x's, 27 was the sum of our y's. What the heck is this going to be? So we have to do inverse sine to get rid of it. 26.4 divided by 27. So let me show you how I've got that calculated in there, like that. So I've got it all as 1, 26.4 divided by 27, and then I'm taking the inverse sine of that. Yeah, you can do it as 2 separate steps if you want to. And then my answer for that is, 77.8, like 78 degrees. It should be a big angle. Look at the triangle. This should be a big angle right there, the sine of that angle. So that means our theta here is equal to 77.89. Now, could I have used tangent? Sure. Could I have used cosine? Sure. We've got all 3 sides of our triangle. It doesn't really matter which one you use. In fact, you can double check it if you really want to. But that means our theta is about 78 degrees. And what direction is it? Okay, 78 degrees from south. Again, 78 degrees from our vertical component right here. It's not 78 degrees from the east, 78 degrees from the south. So this is east of south. Again, it's 78 degrees from south, but you're turning in the eastward direction from south. You're not turning in the westward direction from south. So now we kind of know exactly what we're doing. To do our resultant vector of this, we would go 27 miles at an angle of 78 degrees east of south. So you always have a magnitude, an angle, and a direction. By the way, I've got this summed up in one last spot right here. You may want to take a second. This is what I just talked about in terms of doing all these different steps, in terms of going through all this from start to finish. So you can hit pause right here. I'm going to go away, but you might want to write this down. This is what we just did. We sketched our vectors from tip to tail. We figured out where the resultant was, how long it was, and kind of what angle it was at, so we kind of check ourselves later. We did SOHCAHTOA to figure out the x's and the y's of each of our original vectors. Then we found the sum of our x's, the sum of our y's, used Pythagorean theorem, x squared plus y squared equals r squared. And then finally, we used the angle of our resultant, either SOHCAHTOA, one of those, to figure out what our angle was. So there you go. I know that's a lot. I'll be doing some more of these in our next video. So there you go. Take a deep breath. We'll come back. All right. See you in a bit, you guys. Bye.